So our first two sections in this unit were all about collecting data. Our last two sections, which are going to take us a little bit longer to get through, are going to be about once we have the data, how can we use it, how can we analyze it, and then reach some conclusions based on that data. There are two particularly important measures of data that we need to start by looking at. One is called the mean, which I know you know about and I've been using since middle school, if not before then. And the other is called the standard deviation, which you probably haven't seen before. I know that you know what the mean is, but I want to define it anyhow and then show you a formula we're going to use for the mean, just to get you used to some of the notation in this section. I do want to warn you, the notation gets a little bit weird, but stick with me on this stuff. It's not going to be as bad as it looks. First of all, you know that to find the mean, the average, you just add up all your numbers and divide by the number of numbers. I'm going to say this is the sum of the data entries divided by the number of entries. The sum of the data entries divided by the number of entries. We have a symbol. So actually, first of all, we're going to have a slightly different looking formula if we're trying to find the mean of a population and the mean of a sample. Actually, we find them both in the exact same way. We're just going to use different symbols to represent different things in there. First of all, the mean of a population, I'm going to use a Greek letter to represent my mean. And this is the Greek letter mu. It's kind of like an elongated U. It's pronounced M-U, mu. And actually, we're going to use Greek letters for everything that we deal with that talks about a population. Greek letters, anytime we're dealing with a population. And actually, why don't I complete this right now? I'm going to say English letters. Maybe not English, standard letters when dealing with a sample. I'll show you that in a moment. Mu is my symbol for the mean of a population. I'm going to add up all my data entries. I'm going to say X is a piece of data. In front of the X, I'm going to write a fancy Greek letter, sigma. That symbol means add up all those things. If X is a single piece of data, this sigma means I'm going to add up all the pieces of data that I have. Sigma means sum. We're just going to add up all the pieces of data that I have. When I'm done, I'm going to divide that sum by capital N, which is going to stand for the number of data entries. Again, I know that this doesn't have to be this complicated, but I need to get you introduced to the symbols here, so when we use them with standard deviation, you'll already be familiar with them. My symbol for the mean of a population is mu. I'm going to find the mean by adding up, that's what my sigma means, all the data values, X, and I'm going to divide by the number of data entries that I have. If I want to find the mean of a sample, my symbol for the mean of a sample is X with a little line over it. And I'm going to read this as X bar. That's just my symbol that means the mean of a sample. I'm still going to go and add up all my data values. So I'm going to use my sigma and I'm going to add up those data values. And I'm going to divide by the number of data entries that I have. Going back over here, that capital N is the number of data entries in the population. We have a slightly different symbol for the number of data entries in a sample. It's just a lowercase n, which is going to stand for the number of data entries. In our sample. If you need another moment, press pause and finish copying things down. But if you're ready, we're going to go and we're going to find a mean on the next page. And we'll come back and we're going to fill in the rest of the notes a little bit later. On the next page, I have some numbers here, 6.9, 8.7, 7.6, 4.8, 9.0. We're going to consider this to be a sample. I want to find the mean and the standard deviation. Well, if it's a sample, that means I want to find x bar rather than mu. My formula says x bar equals the sum of all my data values, I'll figure that out in a moment, divided by the, well, n, the number of data values I have, 1, 2, 3, 4, 5, I'm going to divide by 5. Well, the sum of my data values, that's the same as saying 6.9 plus 8.7 plus 7.6 plus 4.8 plus 9.0 divided by 5. Go to your calculator, add those things up, divide, and we'll have our mean. So I'm getting 37 over 5. We're actually going to want a decimal here. So I'm going to say that my mean x bar is 7.4. As for our process, well, to find the mean, we are just going to add up all the data and divide by the number of data values. Add up all the data values and divide by the number of data values. Line over here. We've got our mean. Back on page 16. The next thing we need to define is called the deviation. To deviate means to kind of stray from the regular course. Our deviation is the difference between our data value and the mean. By how much are we differing from the mean? Our deviation is the difference between a data value and the mean. How far is each data point from the mean? Well, if I want to find the deviation from a population mean, my data value is x. What's the difference between that and the mean? Well, our symbol for the mean, if we're dealing with a population, is that mu. So I'm going to say x minus mu. In a sample, my deviation is going to be x minus x bar. Again, it is the exact same calculation. We're just using different symbols based on is it a population or is it a sample. On the next page, what I'd like to do now is find all of my deviations. I want to figure out how far each of these numbers is from the mean. Well, one of my deviations is going to be 6.9 minus 7.4. Go to your calculator, type that in. You're going to get negative 0.5. That's one of my deviations. I want to find them all, though. My next one, 8.7 minus 7.4. Again, go to the calculator. 1.3 is the deviation of 8.7. How far is 8.7 from the mean? It's 1.3 away. How far is 6.9 from the mean? It's 0.5 away. But 6.9 is below the mean. That's why that one was negative. And 8.7 is above the mean. That's why that deviation was positive. Take a moment and go find the remaining 3 deviations. Negative 0.5, 1.3, 0.2, negative 2.6 and 1.6. And now I want to basically find the average of these deviations. Because that would kind of tell me on average, how spread out is this data? How far away from the mean are we? Take a moment and go find your average. Add them up, divide by 5. See what happens. Oh. Hopefully when you tried to do this, you got a sum of 0. Divide by 5. You're going to get 0. And in fact, the average of the deviations will always be 0 because the stuff that's below the mean should balance out the stuff above the mean. That's kind of like where the mean is coming from. So this isn't so helpful, just finding the average of those. I want some other way to take those deviations and get a good average out of them that wouldn't give me 0. This idea of how we can find this is called the standard deviation. Go back to the previous page. Standard deviation is a measure of the average spread. How far are the data values, on average, from the mean? This is a measure of the average spread. How far are the data values, on average, from the mean? We saw that if we just find the average of them, we're going to get 0, so that's not going to be our calculation, but it'll be something relatively similar. My symbol for the standard deviation of a population is a lowercase Greek sigma. This is a lowercase sigma. What I'm going to do is I'm going to take my deviation and I'm going to square it. Because if I square my deviation, in fact, square all, move that up. If I square any particular deviation, it will make it positive. And then I won't have to deal with the fact that while the negatives are canceling out the positives, it will work out nicer. I'm going to find my deviations, I'm going to square them each, and I'm going to add them up. Then I'll find my average. I'll divide by the number of terms that I have. I'll divide by n. Problem is, this is kind of like the deviation squared, average of the deviation squared, rather than the average of the deviations. Well, to undo the square, I'm just going to do a square root of the whole thing. Just kind of go with me on this. I know it's not exactly canceling out, but this is sort of how we're going to deal with getting around that square piece. If I have a sample, my symbol for the standard deviation of a sample is a lowercase s. It's going to work in a similar way. I'm going to first find the sum of all of my deviations squared. So a deviation is x minus x bar. I'm going to square that deviation. I'm going to add up all those pieces squared. I'm actually not going to divide by little n. I'm actually going to divide by lowercase n minus 1 to make this standard deviation a little bit bigger, because this is just a sample, not the entire population. I want a little bit more wiggle room. Don't worry too much about that. Just go with me on this. We're going to divide by n minus 1 over there. Again, once we're done, though, we're going to take our square root of this to cancel those things out. I realize this is a complicated-looking formula. This is not a formula you would ever have to memorize or anything, but I need to show you how to work with this. If you need more time, again, push pause. Otherwise, we're going to go back to page 17. So I now need to find my standard deviation. I need to go and I need to calculate my deviation squared for each data value. I already have all my deviations over here. I now need to square them, and then I'm going to add them up. So this is now the procedure for standard deviation. Step number 1, we are going to calculate x minus x bar, which I already did, but then I'm going to square it for each data value. And add these up. I'm going to calculate x minus x bar squared for each data value, then I'll add them up. Well, all of these things over here that I already calculated were my x minus x bars. So I need to do negative 0.5 squared plus 1.3 squared plus 0.2 squared plus negative 2.6 squared plus 1.6 squared. Go to your calculator, do some squaring. 0.25 plus 1.69 plus 0.04 plus 6.76 plus 2.56, and that should give 11.3. Second thing I'm going to do, I'm going to divide by the number of, this is a sample here, so number of data values minus 1. Divide by number of values minus 1. So I'm going to go do 11.3 divided by, there were 5 data values, so I'm going to go and divide by 4. 11.3 divided by 4 should give us about 2.825. Last thing I need to do. Take the square root. Getting about 1.681. My standard deviation, about 1.681, which is saying, on average, each data value deviates from the mean by about 1.681. On average. Each data value deviates from the mean, differs from the mean, by about 1.681. I want to show you one more example of this. There will be 2 homework problems where you need to go through all these calculations by hand, showing, I mean, you're using a calculator for the arithmetic, but showing the sums and the division, the subtraction problems, the squaring, the square roots, all of that stuff. And then we'll end by seeing how we can use some technology to deal with this if there's like 20 data values, and that would take us forever to do by hand. On page 18, hatching successive game birds is a topic discussed in the book Wildlife Management Techniques. What percentage of Canadian goose nests are successful? Well, the studies gave the various percents of successful nests. So in these various places, in one place, 23.9% of the nests were successful, in another place, 52.5%, another place, 60.0%, and so on. I want to find the mean and standard deviation of this data set. Well, this data set is a sample. These are not all goose nests all over Canada. These are not all goose nests across the U.S. These are Canadian geese, but in the U.S. This is a sample. So I need to go use my sample formulas. First, I'm going to find my mean, my x bar. I'm going to go and add up those data values and divide by the number of values. So 23.9 plus 52.5. Yes, I will need to see this work when you go to do the homework. There will only be 2, maybe 3, where you need to write all this stuff out, but I do need to see these calculations. My formula for the mean is divided by little n, not little n minus 1. So 1, 2, 3, 4, 5, 6. There are 6 things. Go to your calculator, do the addition, do the division, and let's see what happens here. Getting 353.4. I'll divide that by 6. That is 58.9. What this tells us, this is the mean. This is the average. On average, about 58.9% of Canada goose nests are successful. And that sounds weird. We're changing this to Canadian. Goose nests are successful. Normal average. Rather than doing the deviations and the squaring separately, how about I just deal with this all at once? I want to go figure out the sum of all of my deviations squared. Well, let's see. My first deviation is 23.9 minus 58.9. Data value minus the mean. I'll square it. Do it for the next one. 52.5 minus the mean. 58.9 squared. Write out the other 4 deviations squared. I think the next thing you should go do is do each subtraction problem and square the answer. Getting negative 35 for the first one, but then square it, you're going to get 1,225. Take a moment, deal with that for all the others. Maybe push pause, deal with it, and then return to this. When you're done, add them up. $1,868.42 is my sum. I now want to go and figure out the standard deviation. My formula says the standard deviation is the square root of the sum of all of those deviations divided by n minus 1. So I want to go do the square root of 1,868.42 divided by, there were 6 data values, so I'm going to divide by 6 minus 1. Well, go to your calculator, divide that number by 5, and take the square root of your answer. Getting about 19.331. On average, each data value is about 19.331 from the mean. And the point is, the bigger the standard deviation, the more spread out our data is. I think that's all I have to say about that. Now, usually, when you're running an experiment and you have a lot of data value, and you need to find the standard deviation, you have a lot of data values, and it's really not practical to do this stuff by hand. If we were in class, we would now see how to do this on the graphing calculator or the scientific calculator, which we could do But Mrs. Eburn and I thought that it might make more sense, since you're at home and you all have different types of calculators, and it's kind of a pain to teach the graphing calculator this way where we can't walk around and help you guys out. We thought it might be useful to show you how to do this using Google Sheets. In the homework, if the problem says, do the calculations by hand and all that, you're going to do exactly what I did on these last 2 pages. But if the direction says using technology, you're going to use the spreadsheet technology of Google Sheets to do that. Let me show you how to do this. Before I show you, though, please go to page 19 in the notes and read through what it says on the top. The number of U.S. hurricane strikes each decade from 1851 to 2000 are listed below. We want to use technology to find the mean and standard deviation for this data set. This would be a pain to do by hand, plus there's not a lot of room there. Let's see how to do this using technology. So we're going to see how to use technology to find the mean and the standard deviation of a sample. Keep page 19 in your notes in front of you as we go to do this. On the computer, you need to go load Google Sheets. Probably get into your email account, go to Google Drive, and then from Google Drive, you can say new, and we want to create a new Google Sheet. Mrs. Istvan told me you guys have used this stuff in chemistry, so it shouldn't be a big deal, hopefully, to get you here. Looking at that example on page 19, we want to find the mean and standard deviation of that data set of the number of U.S. hurricane strikes each decade. Well, first thing I need to do is enter in all my data. All I'm going to do is type in each data value and enter, and by the time I'm done, I'm going to have a whole column of data values here. I've got 19 hurricane strikes, 15, 20, 22. Go type in all your data values. Once they're in there, I want to find the mean and the standard deviation. I'm just going to type in mean over there in space C1 and standard deviation in space C2, just so I kind of have some labels for what I'm about to do. Then I'm going to click on the cell next to where I put that little label. And I need to use the mean calculation within Google Sheets to do this. I'm going to say equals. The command for the mean, they're not as fancy when they call it mean, they just call it the average. It's the same thing. I'm going to type in the word average. And then I'm going to open up some parentheses. What I now need to do is select all the data values that I want to find the average, the mean of. You're going to click on the first data value, and you're going to drag until you get to the last data value. And I'm going to then close my parentheses. And if this works out correctly, it'll find the average, the mean, of the data in cell A1 all the way through A15. I'm going to push enter. Should give you a mean of 17.6. In your notes, write down that for that first example, your X bar, 17.6. The standard deviation. Well, again, I'm going to say equals to bring up the commands. And the command for standard deviation of a sample is STDEV, standard deviation. The rest of this is going to work out the same. I'm going to open my parentheses. I'm going to click on my first data value. I'm going to drag down to the last data value, so from A1 to A15. Close the parentheses, push enter, and I'm getting a standard deviation, a little s, of about 3.641. Your mean, on average, we're about 17.6 hurricanes per decade, and the standard deviation, 3.641. Each decade, the number of hurricanes differed from the mean by about 3.641. Let's do this again in that next example. I'm going to create a new spreadsheet. We are given the number of gallons of water consumed per day by a small village. This is a sample. We want to find the mean and standard deviation of this data set. First thing I'm going to do first thing I'm going to do is I'm going to type in all my data values. So take a moment, get those in the computer, maybe push pause so you can get them all in, and then you'll resume in a moment. This one would really be a pain to deal with by hand. Should be 20 data values there. Again, I want to find my mean and my standard deviation. This is not necessary, this is just so I remember which is which. To find my mean, my command is equals the average. Whoops, sorry, I did that wrong. Equals the average, you've got to open your parentheses, and then click on the first one and drag down to the last one. Close the parentheses. And we should have a mean of 174.47. Our standard deviation, equals, you've got to first say equals, then STDEV, open the parentheses, click on the first one, drag down to the last one, close the parentheses. You'll get a standard deviation of about 25.642. One more. In the other example on page 19, we have annual salaries of teachers in public schools and private schools. These are salaries in thousands of dollars, so that first teacher is making $38,600 per year, and so on. That's how we can interpret that. Well, we've got two different data sets here, so just to keep them straight, I'm going to enter the public school salaries in one column, and I'll enter the private school salaries in another column. My public school salary is 38.6, 38.1, 38.7, 36.8, 34.8, 35.9, 39.9, 36.2. Get the private school salaries in there, 21.8, 28.4, 20.3, 17.6, 19.7, 18.3, 19.4, and 20.2. Let's see. So, public school teachers, I want to find my mean and my standard deviation. Again, this is just me trying to organize my work a little bit. Then I'll do the same for private school teachers. I want to find my mean and my standard deviation. For the mean, I'm going to say equals. My command is average. Open the parentheses. Click on the first number for the public schools and drag down to the last number for the public schools. Getting an average salary of about $37.375, so about $37,375. Standard deviation equals STDEV. Open the parentheses. Click on the first, drag down to the last. Standard deviation about 1.719. I'm now going to do the same for the private school teachers. Getting a mean of 19.537. On average, private school teachers make about $19,538 per year. First-year teachers there. And standard deviation about 1.41. In part B, on page 19, we're asked what this means. Well, it looks like the average salary for first-year teachers in a public school is higher than the average salary for first-year teachers in a private school, because the mean was higher. And because the standard deviation was greater for the public school teachers, it just means that there's more variability. The salaries differ more from the mean if we're dealing with public school teachers than if we're dealing with private school teachers. In the homework, when it says to use technology, you're going to need to use Google Sheets to go through these calculations.